Alright, so let us start off by recalling these two results from the previous group theory video. This first one measures the sizes of the conjugate classes. Ca denotes the size of the conjugate class containing the element A. And then it turns out that that size is equal to the index of the normalizer of A. And a consequence of this is our class equation, where we understand that this sum runs over a set of elements A, where the set has exactly one element from each conjugate class. Now today we are going to see one of the consequences of this class equation. But before we get to the actual things, we have a preliminary result which is being called a sublemma. So let us first see what this is and let's prove this, and then we will get to the main thing. So what the sublemma says is that a group element A is a central element, that is, it belongs to the center of the group if and only if its normalizer equals the whole group. And in particular, if G is a finite group, then A is a central element if and only if the normalizer and G have the same order. So let us first prove this. We have A belonging to the center if and only if GA equal to AG for all elements G in G, because that's what a central element is. It is something that commutes with everything from the group. But this condition itself also tells us something else. It is equivalent to the fact that G is a subset of the normalizer of A. Why? Say you have this condition. What does that mean? It then means that every element of G commutes with A, and that's why that element would belong to the normalizer. Conversely, if you have this containment, then every element of G belongs to the normalizer, so it would commute with A. And that's why you will have this condition. So that means here we are not looking at simply implications, but rather equivalent statements. But we know that when this happens, then G is equal to NA, because NA automatically is already a subset of G, and conversely also. That is, when NA is G, then of course G is a subset of NA. So we get the first half. In particular, if G is finite, note that this much is true regardless of whether G is finite or not. Here, however, what happens if G is finite? Then this equality is itself equivalent to this equality. But why? Can we think of it for a moment? If you have this, then obviously you have this, provided G is finite. Conversely, if you have this, then combining that fact with this thing, you get this. Okay, so that is why, oh, I said combining with this thing. No, that is not true. Instead, not this containment but this containment. We don't always have this, right? But we always have this. So what does this say? It says that NA is a subset of G, where G is finite. Along with that, if someone also says that NA has the same number of elements as G, then they have to be the same set. That's how we get to this. So that means if G is finite, then this is equivalent to this, because we have this intermediate thing, NA and G being equal. So that is the proof. Now we are going to go to the consequences. These consequences have been named applications of the class equation. So this is going to be application 1. That's how it appears in the text, and the result is this theorem. And the theorem just it says this: if the order of if G is a group, of course we understand that, and it's a group whose order is the power of a prime, p to the power n, where p is a prime, and there is something else, a very subtle, well, it's not that subtle, but it is something that the author has not explicitly mentioned. You will see what I mean. The author just simply writes, if order of G is p to the power n, where p is a prime, then the center of G is non-trivial. That means there will be something in the center besides the identity element. The center cannot have order 1. However, that is not exactly true. What happens if n is equal to 0? In that case, G itself has only one element. So the center automatically has one element in spite of having this form of its order. So we need to additionally assume that n is a positive integer. I think the author implicitly assumes that, but he has not mentioned it. Here, however, we are going to write that n is a prime number and p is a prime number and n is a positive integer. Then the center of G is not equal to the trivial group consisting of only the identity element. Now this fact is important, and it is going to now be proved by the class equation. So the proof is going to go like this. For any element A in G, since the normalizer of A is a subgroup of G, its order should be a power of p, because you see the order of G itself is a power of p. So by Lagrange's theorem, the order of the normalizer has to divide this power, so it should itself be a power of p. More specifically, the order of the normalizer of A should be of this form. P to the power NA, where NA is a non-negative integer. We cannot take positive. NA in general is a non-negative integer satisfying NA less than or equal to n, so that P to the power NA can divide P to the power n. That's why we need this inequality. And why I did not consider positive integer here, it is because among all the elements in G, there is the identity also, no, whose order is 1. That means P to the power 0. So to allow for that NE to be equal to 0, I have considered this to be a non-negative integer. Now, by the above sub-lemma, A is a central element if and only if the order of NA is equal to the order of G. We have just now seen that. That means P to the power NA is equal to P to the power n. And that means NA is equal to n. Okay, so that means we now have this fact that A is a central element if and only if NA is equal to n, where NA is the exponent of the power P to the power NA, which is the order of the normalizer of A in G. Now we are going to write the class equation. Now the class equation of G is, we will need some space, so let me do it there. And that convention goes with the sum, that the sum has that many terms, as many representatives of the conjugate classes we have in the, well, I should not have said as many representatives, but you understand that the sum has one term for each conjugate class. That's what it means. Each A comes from precisely one conjugate class, and from that conjugate class nothing else comes. Now this sum itself can be written as a sum of two sums. One in which we have those A's for which NA is equal to n, and the ones where NA's are strictly less than n, plus Now for these, for the terms in this first sum, each such quotient is going to be 1. Why? Because when this happens, then the numerator is p to the power n and the denominator is p to the power na. They are equal, so they cancel out and we are left with 1. But the question is, how many 1s are we going to get? That is a question that we should answer. And so that means this sum will look like this. But the question is, how many 1s? Let us just keep it like this for now, and let's write the other sum. The other sum can now be written just simply like this: p to the power n divided by p to the power na, so this. And that fact here also continues, that we are considering 1a from each conjugate class, not multiple a's from the same conjugate class. Also, we are not, it's not the fact that we are not choosing anything from some conjugate class. It's not like that. Okay, so let us now look at the types of elements that give us this condition. We know precisely that they are the central elements. Now, if you take a central element, then what happens to its conjugate class? What are the elements conjugate to this element? By the definition of conjugacy, all the elements conjugate to A look like this, where C is some element in G. But due to the fact that A is a central element, this will be equal to C inverse CA, because A will commute with C. So ultimately this will be equal to A. So that means in the conjugate class of a central element, we have only that element itself. And since we are to consider one element from each conjugate class, so in this sum, you will have as many terms, as many 1s, as many terms you have in the center. So this many 1s. Here, however, in this second sum, it's not necessarily the same case. So that means what? Oh, and one more thing, when you are writing something formally, never use this symbol for equality. I have just carelessly written it like this. This denotes the fact that two lines are parallel, something like that. Okay, this does not denote equality. Okay, so that means the equation now takes the form this. So on the left side we have the order of G. On the right side we have the order of the center plus this extra term, extra sum. From the above equation, we get Now look at this final equation. The right hand side is divisible by p. And why is that so? That is because this is divisible by p. Note very carefully that we cannot just simply say that this is divisible by p unless we know that n is a positive integer. If n is equal to 0, this is not divisible by p, because in that case it becomes 1. And that's why in fact we also need in the beginning that n is a positive integer. So now with that condition, this is divisible by p, and each term in this sum is divisible by p. Why? Because the exponent is positive again due to this inequality, na being less than n. So this is divisible by p means the order of the center also has to be divisible by p. Since the right hand side of the above equation is divisible by p, so is the left hand side, that is the order of z. This implies that this has to be greater than 1. Being the order of some subgroup, it is a positive integer, but it cannot be equal to 1 due to this divisibility. And because of this inequality, the center cannot be trivial. It must have some non-identity element, and this is what we wanted to prove. So that's the proof. Now this fact that and this type of groups have a name also, whose orders are powers of prime. The finite groups, they are called p groups if p is that prime. So that means this theorem says that the center of every p group is non-trivial. Now we are going to use in fact this result to have something else, which is a result that we already know, and in fact we proved this very fact that now I am going to state in the exercises, but with much effort. Now it will come out somewhat effortlessly with whatever we have now. If G is a group whose order is again a power of some prime p, but this specific power p square, where p is a prime number, then G is abelian. By the previous theorem, the center of G is non-trivial since G has order p square Lagrange's theorem then implies that the order of the center of G is either p or p square. because it has to divide p square, so it can either be 1 or p square, but it cannot be 1, and that follows from the previous theorem. So now if we can show that the center has order p square, then it will be equal to the whole group and the group will be abelian. But what happens if its order is say p? So let's suppose that if the center is of order p, whereas the group has order p square, that means the group is larger than the center. So we can choose a non-central element, something from outside of the center in the group. Okay, now we are going to consider the normalizer of this element A. Note that the normalizer of this element, should I write all the things at once? Let me do that. Why not? Note that, let me write it here. The center of G is a subgroup of the normalizer of A, and that also is a subgroup of G that we already know, but additionally it is not equal to G. How? Let us first see why we have this though. You take any element in the center, say B, that means what? B commutes with all the elements of G. In particular, B also commutes with A because A is an element of G, but that means B belongs to the normalizer of A. So any element in the center belongs to NA. That's why we have this containment. And why is this containment a proper containment? Why is NA a proper subgroup of G? That's because A is a non-central element. We already saw in that sublemma that NA is equal to G if and only if A is in the center, but A is not in the center. That's why we have proper inclusion, proper containment. Okay. Now just like the center, the normalizer is also a subgroup, so its order also has to divide the order of G by Lagrange's theorem. And at the same time, since the center is a subgroup of the normalizer, its order also has to divide the order of the normalizer. Since NA is a subgroup of G, we must have a P dividing the order of NA, and this divisibility comes from the first containment, and the order of NA dividing P square, but it is not equal to P square. So then what choice is left for this number? Namely that it has to be equal to P, that is the only choice. Thus we must have but then you combine this fact with this containment to conclude that the normalizer actually has to be equal to the center. So the normalizer is equal to the center, since A commutes with itself, so A belongs to the normalizer of A. And this is a contradiction because we chose A to specifically to be a non-central element, and we have ended up proving that it belongs to the center. This cannot be. So that means our supposition is wrong. What did we suppose? We supposed that the center has order P, which cannot be true. So our last supposition is wrong, i.e. the order of the center is not equal to P. Thus, we have to choose the only possibility left for us, namely that the order has to be equal to P square. And hence the center is equal to the whole group, or the group is abelian. This kind of things are in fact what makes the theory of finite groups so strange and beautiful. Just the number order of the group determines whether it is abelian or not, if it is of a special type. So that is the proof. If you go back to some of the previous sections, there we have some 3 or 4 exercises using which we proved this same thing. But it took quite a lot to prove this fact that any group whose order is P square is abelian. But now it comes out as a fairly easy consequence of the class equation, or a consequence more directly of that result, that theorem 2.11.2. So let me just keep things till this itself for tonight. Now the application 2 that we have is Cauchy's theorem for any finite group. If you can recall, we have already proved Cauchy's theorem for finite abelian groups at the end of that section where we study homomorphism. But now, using in fact that result and class equation and using induction, we can prove Cauchy's theorem for any finite group. Let's recall the theorem just briefly. It says that if G is a finite group whose order is divisible by some prime P, then G has an element of order P in it. So that is Cauchy's general theorem for any finite groups, which we will prove in the next group theory video. And our next upload today is, what is the day today? Tuesday. Our next upload is this coming Friday. And on Friday, what shall we do? Groups. Let's do vector spaces. So see you on Friday with that. In vector spaces, we are doing inner product spaces, right? So we are going to see those things. So with those things, let's see you on Friday. Until then, this is me, Lucifer from a mathematical room. Have a nice night.